Welcome to The Explainer. Today, we're diving into something called natural deduction. It's a system of logic that didn't just change how we think about proofs, it actually revealed this wild, secret connection between a mathematical argument and the computer programs running our world. So it all kicked off with this one big question that was bugging logicians for years. How can you create a formal system for logic that actually feels like how we think? You know, something that isn't just a cold, rigid, mechanical checklist.
And this whole quest for a more human-friendly logic led to a completely new system. This one was built from the ground up to really capture those intuitive leaps, those what-if moments that we use all the time when we're building an argument.
Right, and that was the absolute core of it. The whole point was to get away from these systems that just check if a proof is right at the end. Instead, they wanted a system that showed the journey of getting there. You know, the creative, sometimes messy process of how a real argument comes together. What's pretty amazing is that the solution came from two different logicians working totally on their own in the very same year. And then, decades later, a third came along and basically tied it all together, building the foundation for a whole new way of thinking.
So check this out. 1934 was just this landmark year for logic. You've got Stanisław Jaśkowski and Gerhard Gentzen, who, without knowing about each other, come up with the same fundamental idea. Then, you fast forward to 1965, and Dag Prawitz drops this study that basically becomes the Bible for everything that came next.
And even though they were chasing the same thing, their methods had their own unique flavors. Jaśkowski came up with this line-by-line approach that you might actually recognize from a logic class today. Gentzen's version, on the other hand, was structured in a way that was just perfect for doing a really deep theoretical dive into what proofs even are.
And this is where Prawitz just becomes so important. See, he didn't just tweak the system, he uncovered its deepest secrets, like this incredibly powerful idea called the normalization theorem. His work literally created the bedrock for the entire field we now call general proof theory.
Okay, so what is this elegant engine at the heart of natural deduction? What makes it feel so, well, natural?
Well, the whole system is built on this simple but really powerful two-sided idea. For every logical building block, like and or if-then, you have two types of rules. One set of rules is for introducing it into your proof, and the other is for eliminating it so you can use it to figure something else out.
Let's think about it like building with Legos. The introduction rule for and is simple. To build the A and B structure, you first need to have the A brick and the B brick. Makes sense, right? Then, the elimination rule is how you use what you've built. Once you have that A and B structure, you can snap off the A piece to use it, or you can snap off the B piece. But, and this is a big but, this whole thing would fall apart if the rules were just random. They have to be in this perfect balance called harmony. It's a principle that basically says your elimination rules can't pull more out of a statement than your introduction rules put in. It keeps the whole system honest.
Okay, so here's where things get really interesting. This elegant system for logic was about to cause a massive explosion in a totally different field, computer science.
Hey, remember that normalization theorem from Prawitz? Well, it proves that any proof, no matter how messy or roundabout it is, can always be simplified. You can get rid of all the useless steps, those logical detours like proving A and B just so you can immediately say A. You can always find the most direct path. I know, that might sound like a super abstract way to just tidy up proofs, but it turns out that this little property has a stunningly direct and practical connection to our digital world.
And this is the big one, the total game changer. It's an idea called the Curry-Howard correspondence, and it's the profound discovery that a proof in this logical system and a program in a certain kind of computer language are, well, they're the exact same thing.
So let's just break this down, because this is the core of it all. A formula in logic, like A implies B, is the same as a data type in programming, like integer or string. A proof of that formula is actually a program that gives you a result of that type. And that whole process of normalization, of simplifying the proof, that is literally the same thing as running the program.
So as you can imagine, the impact of this idea has been immense. The core concepts of natural deduction have just spread everywhere, becoming this super powerful tool in a ton of different areas. I mean, this system proved to be so fundamental that it became the blueprint for formalizing all sorts of other reasoning. People have adapted it for everything from the bizarre world of quantum logic to systems that try to make sure a conclusion is actually relevant to what you started with.
And all of this leaves us with a really fascinating, kind of mind-bending final thought. If finding a proof is the same thing as writing a program, does that mean a mathematician who discovers a new theorem isn't just uncovering some truth that was already out there, but is actually inventing a brand new computational process? It's a question that totally blurs the line between discovery and creation.